Okay, so we're going to look at our next conic section, which is the ellipse. And if you recall, just kind of a little reminder that the general form of any conic section is this guy. Typically, our A is going to be a positive number, and typically our B is going to be 0, which would eliminate that term. Okay, so we're almost always exclusively working without this term. Another reminder is we do need that there, though. We need to think about the B because that is how we determine if it is an ellipse or if it is, we do the determinant, right? B squared minus 4AC. Sorry, I said determinant, discriminant. And that, depending on if it's bigger than 1 or less than 1, we know if we have an ellipse or if we have a hyperbola or whatever it is. So for the case of the ellipse, the discriminant would be less than 0, meaning negative. Okay? But this is a little better kind of, we could find the discriminant and think of it that way, but here's another way to tell if there's an ellipse. This should be a C, by the way, here. All right? If A and C are both positive, so we're looking at the x squared term and the y squared term. They're the only terms that are squared, right? So if we're looking at the two squared terms, if the A and the C are both positive, then we have an ellipse. And a positive A and a positive C here would make this a negative number, which is less than 0. And of course, this part is always 0 for us because B is going to be 0. So this is another way to think about it. Just if A and C are both positive, but they're not equal, we have an ellipse. If they are equal, that's a special case of an ellipse, which is a circle, which we did a little bit last time, okay? These are just reminders. If A and C have different signs, then you have a hyperbola. So if these are one's positive and one's negative, right, then you have a hyperbola. And then if there's only one squared term, so if either one of these is 0, like let's say that term's not there, you have a parabola. And if this one is not there, whoops, then you have a parabola as well. So that's just a reminder about general form. Moving along, how do you define an ellipse? Well, it came from this idea that we had these 2 points. This was in that Think Well video, the first one you watched the other day. If we tie a string between them and the string has a lot of slack, and then we take our pencil and we put it in the string and we start keeping it taut and draw our pencil around, it would kind of do this. It would make this kind of a shape. All right, and that gets at our definition. Now, because the string never changes, we could call that length A and that length B. We know that A plus B will always be the same number no matter where I am. Let me show you what I mean by that. Here's an A and B. If I add these together, let's say we get a length of whatever this string is, right? This string has a length. Let's just say it's 12 inches long. A plus B will be 12 when I'm here on the ellipse, right? It's always going to be 12 because the string was 12 inches long. If I'm at a different point on the ellipse, say down here, B is now this and A is now that, A plus B will still equal 12 because the string is still 12 inches long no matter what. So that's key to the definition of an ellipse, that A plus B is always the same, okay? And actually, I don't know that I should call that A and B because we use A and B to mean other things. So I'll just call it like, let's see, M and N, okay? So M plus N will always be the same number. That was from that Think Well video as well. We also know we get it from the way that we slice a conic section. All right, so here's our definition of an ellipse. It makes this egg-looking thing. One of the more famous ellipses is the path that the Earth takes, the orbit of the Earth around the Sun. It's elliptical. So we're going to define it. It's an ellipse is the set of all points in a plane that the sum of whose distances from two fixed points is constant. The sum whose distances from two fixed points is constant. So that's this thing up here, like what we just said. The sum of the distances back to these 2 points that are fixed, they're nailed in. The distances, the sum of those is always the same, and we get this ellipse, okay? Those 2 points, the 2 like nails, are called the foci. So we see that here, they're in green. And a line segment through the foci is called the major axis. It connects one end of the ellipse to the other. All right, so that's, I shouldn't have traced over it because I want to keep the colors. That's that red segment, okay? It intersects at the vertices. Those are called the vertices. So when we have an ellipse, these are not vertices. Those are not vertices, here and here. Not vertices, okay? The midpoint of the line segment joining the vertices is called the center. So we're kind of working everything on the major axis, the long way. This is like an oblong shape. One axis is larger than the other. So again, when we have this ellipse, we've got one axis this way and one axis that way. So one of those axes is called the major axis and one is called the minor axis. Let me do them in the same colors. So the major axis just means it's the long way, and the minor axis is the short way. So yes, we could have an ellipse that goes this way, in which case I'll do the major axis in red again. The major axis is that guy, and now the minor axis is that way. And if I draw it the other way, the vertices are now here and here, because the vertices are always at the end point of the longer axes, okay? The foci are always on the long axis, all right? So there's a major axis and a minor axis. The point right in the middle is the center, called the center, okay, of your ellipse. And then we have our minor axis, all right? So just like the other conic section, the circle, this is our general form, but when we want to graph and stuff, we have something called the graphing form. This is typically the graphing form of the ellipse, okay? A and B are the distances from center to the endpoints of the major and minor axes. So if I draw one this way, let's say, I have my center here. A is going to be this distance, and B is going to be this distance. Why did I choose A and B how I did? Because A goes in the X direction, and I know that because it's underneath the X term. The B goes in the Y direction, or vertically, because it's under the Y term. All right? Always, always, always equal to 1. And it's always going to be plus because we're assuming our first term is positive. And the whole point of an ellipse is when the A and the C match, right? So the number in front of the X squared is positive and the number in front of the Y squared is positive. So we're looking at these where it's always, always, always plus between them and equal to 1. All right? The center, foci, and vertices are all on the major axis. So this time on this one, I'll draw it this way. So there's my major axis. The center is on the major axis. It's also on the minor axis. But the foci, which are here and here, are on the major axis only. They are not on the minor axis. And then the vertices are the endpoints of that major axis where you're actually on the ellipse. All right? To find the location of the foci, we have this equation. I can show you a derivation of it. I promise there is one. I can show it to you in class. It's not something we want to do in this video. We want to keep this video to a reasonable length. But remember that A is this distance here, and then B is that distance here. And notice the formula switches. It's going to depend on which one's bigger. If the A is bigger than the B, or the B is bigger than the A, and it depends if I have an ellipses that I'll say has a vertical orientation or one that has a horizontal orientation. Then there's something called eccentricity. We talked about this in class when we did circles. A circle is a special case of an ellipse. It has an eccentricity of 0. So the eccentricity of an ellipse can range from 0 to 1. When the eccentricity equals 0, you have a circle. On the other side, the eccentricity can only approach 1. It doesn't actually get equal to 1 because that would kind of, well, that would do something to our ellipse. We're just going to say it can approach to 1. I am not 100% sure on this. I just sort of made that up just now thinking about it, but I'm going to say that you can't really get to 1, otherwise you have a different conic section. So I'll verify that and talk about it in class. How do we find the eccentricity? It's the ratio of C to A. Now we have to define this distance C. So if I draw my ellipse like this, here's my foci. The distance C, oops, hey. The distance C is the distance from the center to a foci, and the distance A is the distance from the center out to the vertex. I'll call that A. Now in this case it's A. We always do it on the major axis, so it could be B if I have an ellipse drawn that way. If I make the ratio C over A, I get my eccentricity. So when I look at a fraction, we said that it's always going to be less than 1. That's because C will always be smaller than A. It's just always going to happen. So I could have like 1/2, or I can have 2/3, or I can have 5/6, or I can have 1/100th. Which one of these eccentricities is closest to 0? This one. That would mean that the distance from the center to the foci is 1, but then the distance to the center to the vertex is 100, so it might be all the way out here, right? So when it gets closer to 0, that means that this foci is getting closer and closer to the center, so this thing will look very circular. When the foci actually lines up on the center, that means the distance between them is 0, which means the numerator is 0, which makes that number 0, meaning the eccentricity is 0, because when this becomes 0, the distance between the foci and the center. All right, we're not going to focus too much. Oh, I get it. Focus on eccentricity. We're going to look at graphing these and giving the location of its foci. So this is in our graphing form, which was nice. Remember, this was considered our a squared. This was considered our b squared. There is a plus in between. That's how I know it's an ellipse. We know that our ellipse is always centered at 0, 0. And now the square root of 25 is 5, so a is 5 and b is 3. So which one is bigger? The one underneath the x squared is bigger, so the major axis goes 5 in both directions. Why am I going in the x direction? Because it was in the x term, the bigger one. So those points are on the ellipse. And then b is 3, so I go in the y direction because that was grouped with the y. And there we go. I can graph my ellipse. Mr. Tong, do you have a second? So I can graph my ellipse here. 1, 2, 3, 4, 5, 1, 2, 3. So I didn't space them out evenly, so it looks horrible. But there it is. That's how we graph it. I just got to check with Mr. Tong on this one. I think that's the only thing we need to graph. Then they do want the foci. We do want to know the location. If I'm graphing an ellipse, you're on video or audio. The only thing I got to really do is graph the center and then find those points, right? Correct. That's enough to graph it?
Correct.
Okay, cool. Thanks. We do want to find the location of the foci. So that was those formulas before where we said C equals the square root of a squared minus b squared, or C equals b squared minus a squared. Basically, all you do is you take the bigger one minus the smaller one. So I've got the bigger one is the a, so we would do a squared minus b squared. Remember, we already have a squared is 25. That was in our equation. Minus 9, I get, what, 16? So the square root of that is 4. So the foci for these guys are right there and there. And they're always on the major axis. So remember that just represents, it's always the bigger minus the smaller. We square root it, and that's the distance, whoops, from the center out to the foci. So that's that distance of 4. That's how we locate the foci. We actually want the location, meaning we want the point though. So I got to find those coordinates. The coordinates of that are, well, it's always on the major axis, which has a y coordinate of 0. So I know both coordinates are 0 for the foci. Then I move out from the center on the major axis. I go 4 in each direction. So that's actually the location of the foci, and I have my graph. All right, let's try the next one. So to graph this one, we know it's centered at 0, 0. So this guy, this square, I want to find like my semi-axes, like the half of the axes. So I square root this guy. We know our a squared. We know our b squared. So if we square root them, a is 2, b is 6. So now the bigger one is underneath the y, or it's in the y term. So we're going to go 6 up and 6 down, and that puts us on the ellipse. Our other axis goes 2 in each direction. All right, so comparing these two, by the way, which one is more circular? This one here is more circular, so its eccentricity is closer to a circle, and a circle is 0. So that's just something to note. Oh, I shouldn't write factorial. Is closer to 0. I like to think of it as a comparison like that. All right, so we've got our ellipse down here. Graph. Now we just need to find the foci. So the foci is always the square root of the bigger one minus the smaller one. So I square the b, I square the a, I get the square root of 32. Can I simplify that? 8 times 4. So 16 times 2 is actually better. So I got 4 root 2. Right? So I go in the major axis direction, 4 root 2. Whatever that is as a decimal, it's going to be more than 4. 3, 4, and maybe even a little more than 5. I'm not really sure. I'd have to calculate the decimal. Hold on. So yeah, it was 5.65 about. So I go up 1, 2, 3, 4, 5, and then a little more. So the foci are right near the ends because I made this one pretty oblong. All right, so there's your foci. Now they want the location. Well, they're on the major axis, so I know the major axis has an x value of 0, so they're both going to have an x value of 0. And then I'll give the exact values. It's going to be 4 root 2 and negative 4 root 2. Those are the two foci. All right, now let's look at this one. Everything seems to be the same as like our previous ones. We're pretty good. We've got our a squared. We've got our b squared. So we know a is 3. We know b is 2. It's equal to 1, so we're good. It's addition. It's an ellipse. But this guy in here is something different. So what does that do? Well, if we go back to transformations of functions, that's just going to translate or slide our function or our graph down 3 because you're doing the opposite because it's grouped inside with the y. So normally the center is at 0, 0. Now it's going to be shifted down 3. So that is our new center point. Okay? It's not shifted left to right at all because it's still just x squared. You could think of that as x minus 0 squared if you like. All right, so now from that center, which one's bigger? The x is bigger, so this one's going to have the major axis horizontally. So I go 3 units in either direction. And then now vertically, I go 2 up from the center. Here's our ellipse. I'm terrible at drawing these. So that's our ellipse. And now we need to find the location of the foci. So it's going to be somewhere on our major axis, right? Actually, let's make that axis like kind of a dashed line. There's our major axis. All right, so the foci are going to be the square root of the bigger one minus the smaller one. So it's root 5. So what decimal is that approximately? Let's do that here on the calculator. Root 5, 2.2. So if I go 2.2 in either direction, it's like right there. 1, 2, it's like right there. So the coordinates of that, well, they're on the major axes, right? So if I just draw that in, I know that has a y-coordinate of negative 3. So I know that they're going to have a y-coordinate of negative 3, the foci. And now how do I find their x? Well, I already got their x-coordinate. It's going to be root 5 and negative root 5. All right, so next one, we want to graph this guy. So we're going back to now, it's given in this general form like this guy, right? So we've got to convert it to graphing form where we can get information out of it. Before we start, I want to remind you how you can tell it's an ellipse. A is 16. B is 0 because it's missing the xy term. And C is 1. Right? So we said, like, if you do b squared minus 4ac, that should come out to be less than 0 or negative. So b squared is 0 squared minus 4 times a, which is 16, times c, which is 1. It's going to be 16 times negative 4. It's going to be a negative 64. That is negative or less than 0. That's what makes it an ellipse. If we go back to kind of our easier way to think about it, if a and c are both positive but not equal, if they were equal, it would be the special case of a circle. So we can see that A is positive, C is positive. That's how we know it's an ellipse. Remember I said before there's a plus between them? That's really the key. That's what makes it an ellipse. And since they're not equal, it's not the special case of an ellipse, which is a circle. All right? So from here, we want to put it in graphing form. So the first thing is, for graphing form, it has to be equal to 1. So we're going to add 16 to both sides. Right, because graphing form was this. It's got to be equal to 1. That's the key. So I subtract 16, and now I want to make this guy a 1. So I'm going to divide both sides of my equation by 16. So what I get is x squared plus y squared over 16 equals 1. That is now in graphing form. I could think of this as like over 1 if I like. So let's go ahead and graph this thing. So the center is at 0, 0. And then I go, this is my a squared, this is my b squared. So my a is 1 because it's the square root of that. My b is 4. So in the x direction, I go out 1. In the b direction, I go 4. This thing's going to be pretty oblong. So my eccentricity will be closer to 1. It's not going to really be near 0. This is not circular in the least. Okay? So then when I draw this thing, it's going to be a very long and skinny surfboard-looking ellipse. If I spaced my axes properly, it would look a little better. But there it is. And we also need the foci. So we know they're going to be, well, they're on the major axis, which has a y-coordinate. It's x-coordinate of 0 because it's at x equals 0. So I know the foci are 0 and 0. And then what we do is we do the bigger one minus the smaller one, the square root of it. So it's square root of 15. That does not simplify at all. Root 15, negative root 15. There's our foci. All right, moving along. This one looks like it's almost in graphing form, except it's got to be equal to 1. It can't be equal to 36. So I got to divide everything on both sides by 36. So on the left side, there's 2 terms. So like divide everything by 36. A lot of times, these will reduce on the left side where the numerator just becomes 1. So 9 into 36 is what, 1/4? 4 into 36 is 1/9. And there's my 1. Yes, it's in the proper form. And now I can go graph this. So we start graphing this thing by saying the center is usually at 0, 0. But hold on a second. Alert, alert. This means there's been a translation. So if we think back to our transformations of functions, right, these numbers are grouped inside with the variable, so they do the opposite. So this means we're going to go right 1 because it's grouped with x, so it goes in the left-right direction. So I go right 1. And then this one says that I'm going to go down 3 because it's grouped with the y, so we go down 3. Okay? That is my new center. Now I do all the other stuff as planned. A squared, b squared. So a is 2, b is 3. So 2 is underneath x. So in the x direction, I spread out 2. In the y direction, because 3 is underneath the y, I spread out 3. 1, 2, 3. 1, 2, 3. Again, I didn't really space these well. So it's a little harder to see because I didn't do my spacing great which one's the major axis, but it's clear because the 9 is bigger. So I'm just going to draw on my major axis like that. So there's our graph. And then we want the foci. So the foci are 9, the square root of 9 minus 4. So that's going to be square root of 5 again. Was it 4 and 9 last time? Or wherever it was? Yeah, 9 and 4 again here. So notice it's the same thing. It's just in the other direction because this is oriented vertically. So I know that my x-coordinate now, so I need the coordinate of my foci. They're going to be here on the major axis. So I know because this thing goes vertically, the major axis is on x equals 1. So my foci are going to have x-coordinates of 1 for sure. The y-coordinates are going to be negative root 5 and positive root 5. Last one. How long is this? All right, it's going to be under 30 minutes, I hope. Let's go for it. How do we convert this into our graphing form? Holy cow. All right, first of all, the constant can't be there. It's got to get kicked out to the other side. And we want to do we want to complete the square, make a perfect square trinomial. So I'm going to group the x's together. So 9x squared minus 36x. I'm going to leave some, I'll just write it, plus 25y squared plus 50y equals 164. By the way, how did we know this was an ellipse? You just pay attention to the squared terms, right? They're both positive, right? And they're not the same. If they were both 9, then it would be a circle. Or if they were both 25, but they're not. They're different, so it's an ellipse. All right, so moving along here, we want to write it in graphing form, which means I got to have it written something like this squared and then something y squared. So I've got to make perfect square trinomials. So I look at this trinomial first. It's really just a binomial. I got to factor out the 9. Then I'm going to leave some space to turn it into a trinomial. This next one, I'm going to factor out the 25. Leave some space to turn it into a trinomial. And now I want to complete the square to make this a perfect square trinomial so that I can factor it. I'm not going to review how to do that. I'm just going to do it. You remember it from Honors Algebra 2, I am sure. So I'm going to say I add 4 here. I add 1 here. And then I have to add the same things on the other side. So I don't add 4, I add 36 because it was 4 times 9. And then 1 times 25. So I got to also add 25. All right, so now we're on our way here. We've got 9 times this perfect square factors into x minus 2. Plus this perfect square factors into y plus 1 equals 164 plus 36 is 200, so 225. So we're getting closer. We need this side to be 1, right? So I can divide everything by 225. So this should reduce. 9 goes into 225 some number of times. I'm going to need the calculator for this one. 225 divided by 9, 25. And then 25 goes into 225 9 times. So when I rewrite, I've got x minus 2 squared over 25 plus y plus 1 squared over 9 equals 1. That is in my ellipse form. Remember, it's an ellipse because we got a plus in between there, and these numbers are not the same. So now we got our ellipse thing going on, so we're going to graph it. The center starts at 0, 0 normally, but there's been a translation, right? This guy and this guy. So this means that the center was at 0, 0, but now it's going to be at 2, negative 1 is our center. If you understand what's going on inside the green parts here. If not, we can talk about it in class. All right, so there's my center. That means my A is 5 and my B is 3. So A goes in the X direction, so I go out 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 in both directions, and I'm down here on the major axis. B goes up 3, so 1, 2, 3, and then down 3 there. So here's my ellipse. I have it graphed. Are we going to be under? Let me check the time. 2956. No, we got to find the foci. So they're going to be on this major axis. So that looks like Stewie. They definitely have a y coordinate of -1. And then I got to do 25 minus 9 and the square root of that, which is 4. So it's going to be at 4, -1, and -4, -1. Darn it, I didn't beat 30 minutes. 30 minutes and 20 seconds.